Okay, so let's continue. So let's briefly review what we covered in the last lecture. Okay, so in the last lecture, we talked about reconstruction, and then we talked about the maximum information rate in the band-limited channels. Okay, so remember that, right? So far, although we're kind of going into the the realm of digital communications, but technically nothing is digital yet, right? They're all continuous signals, right? It's not like really discrete time signal. Okay, so yeah, we're going to talk about that very soon, but just be careful, right? So here, everything is still continuous time, right? It's not discrete time. All right, okay, so basically the idea is that, so in practice, so we cannot recover our original signal using the sync interpolation, right? Due to some reasons, right? Like, it's infinite in the time, it's not time limited, right? It's infinite in the time domain, right? And it's not causal, right? So yeah, therefore, in practice, there's no way to implement the sync interpolation, okay? So then we need to seek for something else, right? So here, basically what we do is that, yeah, when we get the sample signal, right? And then we use another pulse, it's called P, so as the reconstruction pulse, right? And clearly, P is very practical, right? So we give you a few examples of P before, like the triangle, right, which corresponding to the linear interpolation, and we give you like this rectangle pulse, right? Either it's wide or it's narrow, okay? There are some advantages and disadvantages of those kind of pulse, okay? And clearly, since it's not the sync interpolation, so the reconstruction is not going to be perfect, right? So we have some distortion caused by P, right? And we also see some kind of distortions in 2 lectures ago, right? Like, sometimes, it's kind of, it's not perfect flat, right? It's kind of like this round distortion that is not ideal, right? And the way to deal with that is basically use filtering, right? So basically, we introduce a filter called EF, so to compensate the distortion caused by the pulse, reconstruction pulse, right? All right, so basically, yeah, if we consider the signal in the frequency domain, and let's say this is our goal of reconstruction, right? So this is the original signal, and this is nothing but a time shift in the time domain, right? Because we want the signal to be causal normally, right? So we need to shift the time a little bit. So in frequency, it's a phase shift, right, by T naught. Okay, very nice. And in order to remove the impact of P, so the idea is very simple. We just need to make sure so this multiply that equal to 0 in the baseband, right? And of course, it will be 0 in the higher frequency, right? So it's exactly like this, right? So basically, what we do is that so here, so it's 0, right? Because when at least it has to be a low-pass filter, right? Even in the ideal case, like the sync interpolation, it has to be an ideal low-pass filter, right? So for higher frequency, it has to be 0. But for the lower frequency, right, especially when f is less than the bandwidth of the signal, then we need this, right? We need to get rid of the impact of this, right, but multiply the inverse of it, right? That's it. And then, so we need some constant here and then a time shift, right? So and then we're done. Okay, the idea is very simple, but the requirement is that, so this guy has to be non-zero, right, within this range, okay? And we can see that for the rectangle pulse, it is doable, right? The narrower the better, but it's very doable, okay? Especially, why we need, sometimes we want, so why we want the narrower rectangle pulse for the reconstruction, right? Because when the time domain is very narrow, then in the frequency, it's almost flat, right? It's wide, right? It's almost flat. If it's almost flat, then, so this guy is gone, okay? And we just need this kind of filter, which is very easy to do, okay? So that's basically the reason, right? This is the non-ideal reconstruction of the signal, okay? Of the original signal, okay? And then we talk a little bit on how to characterize, how much information we could transmit, right? And want to relate, so this quantity to the quantity of the bandwidth, right? So normally we say, okay, so if our channel can offer more bandwidth, then we can transmit more, right? What do we mean by that? Exactly. This is what we mean, okay? Because if we use the Nyquist sampling rate, so basically we can sample 2 B symbols per second, right? Where B is the bandwidth, okay? And if we have more bandwidth, we can sample more, right? And here, so basically we say if we sample more symbols, then we can transmit more information, okay? And if it's a DSP signal, right, then our bandwidth is halved. Then so basically we can transmit this much of information, okay? And then here and then we say, okay, so normally in practice, so for each symbol, we're going to use some digit to represent it, right? So and we're going to talk about that today in a bit more detail. But the idea is as follows, right? So let's say if we have 8 levels to quantize the signal, okay, and then for each level we can use 3 digits to represent it, right? Like this. Okay, in this case we in total we have 8 symbols, and we need to use like 3 digits to represent these 8 symbols, right? And in this way we can characterize for each symbol. So we have 3 bits, right? So and computed by this formula, log 2 of m, where m is 8, so small m is 3 in this case. Okay, in this way, and by using that, now we say, okay, we can transmit like B symbols per second or 2 B symbols per second, and for each symbol we can carry like 3 bits, right? In this way, we can transmit B times m bits per second. Okay, so now we relate the bandwidth to how many bits we can transmit per second in practice. Okay, yeah. So yeah, we're going to see this formula again. So yeah, we're going to talk about what exactly mean by this. Okay, and here are some examples that we never talk about this, but later on we're going to see. Those are it's called what's it called? It's called yeah, I forgot the name of it. It's called MC. Who heard of it? Yeah, I always use a short name for it, but I cannot remember it. So what is that? Yeah, never mind. I'll check it. I forgot. But so basically, so this is yeah. So in academia, I think it's called constellation. Okay, so but it's called something else. It's called MC something. Yeah, I forgot. Yeah, it's called constellation in academia. So basically, it means that if it's QPSK, so it can carry 4 kind of symbols, right? So it's 2 bits, right? And if it's 16 QAM, QAM is the QAM that we have seen before. Okay, we're gonna see. If you still remembered when we talk about QAM, quadrature amplitude modulation, right? In the amplitude modulation, we say, okay, the main use of it is for digital communication, right? And here is what we mean. Okay, so basically 16 QAM basically means that we have 16 symbols and we can carry 4 bits of information. And 64 it means that we can characterize 8 bits of information. No. 64 is how many? 6 bits of information. And 256 is like 8 bits of information, right? And now I think for Wi-Fi, you can have up to like 1024 bits of information. And also in Wi-Fi, so basically the bandwidth of the channel is either, it can go from 20 megahertz up to 160 megahertz. Okay, and so basically, by using this formula, you can compute how many bits we can transmit for Wi-Fi. Okay, yeah, is there any questions? Okay, great. So yeah, if we don't have any question, yeah, let's continue. Okay, I'll leave it like this. really bothers me. Yeah, let me check. Yeah, I cannot find it. Oh, never mind. Okay, yeah, let's see what we're going to cover today. So, okay, so for today, the first topic is a non-ideal or practical sampling. Okay, so basically, as we said before, so we solve one problem, which is a non-ideal reconstruction, right? We say we cannot use sinc function to do the interpolation, so we need to do something else. But here, so we didn't talk about the sampling, right? Remember, so what we do here, we use the impulse, the delta impulse sampling, right? And that cannot be implemented in practice because we need the delta function, which does not exist in practice, right? So we need a better, or in other words, right? So we cannot get one point out of the function directly, okay? So we need to do something, to get this sampling, right? So we're gonna say, okay, how can we replace this delta signal, right? How can we get the practical sampling? And then we're going to talk about pulse modulation. So basically, now we're kind of trying to go from the analog communication to digital communication step by step, okay, and see how we can get there. And after this, I think we're almost there. And then, so we're going to review the advantages of digital communication. Right, we kind of mentioned those things briefly before, but now we're going to a little bit more details on that. And from here, we also want to see the desirable properties for digital communication. Okay, so basically, yeah, from the pulse modulation, we're gonna see a little bit that it's not all advantage for digital communication. We have some disadvantage as well, right? And how can we conquer those disadvantages, overcome those, right? Yeah, and probably we should have time to cover the first two topics. And if we don't have time, so we're going to talk about that in the next lecture, okay? Yeah, those are kind of conceptual. It's not mathematical, right? Let's see the first topic. So the non-ideal reconstruction. The non-ideal sampling. Okay. Yeah. Yeah, as we explained, so in practice, we cannot get delta signal, right, to sample this function exactly, right? So let's see what we can do in practice, right? So basically, in practice, what we can really do is as follows. So when the signal comes, right, so what we do is that we cannot get the exact point of the signal, right, like this. So when the signal comes, right, so we cannot get exact point of the signal, but what we can do is that, so we can, the reason of that is that, so normally in practice, we can use a kind of capacitor, to do the on-off sampling, right? And when we do it, it takes some time to make it on and off, right? And if we use a capacitor, so it's like, the time matters, right? It charges, right? The time matters. So basically what we do is that, what we can do is that, instead of getting this point exactly, so we get a small piece of this guy, okay? And then, because we use a capacitor, for example, and it charges, right, by this much, right? So basically, we get the integral of this guy in practice, right? So this is doable, right? Get the exact point is not doable, but this is what we can do in practice, right? So now the question is that good enough, right? Is that equivalent to do a is that equivalent to a delta sampling in practice? Okay, so we're gonna find out. That clear? Okay, so in other words, in practice, so what we can do is like like this. Okay. So mathematically, so in practice, what we can do is as follows. I denote this guy, the sample signal by G1, right? So we're going to explain that in very detail later. Just bear me for a moment. But this is the output, right? This is our sample signal. Okay. So normally that equals to this. So where TQ can be understood as the width of it. Yeah, right. So we do a little bit averaging here. So the averaging here is basically described by a integral. Okay, we integral over this range. Okay, and or we can design this shape a little bit, right? Because the value of the integral and the value of this point is definitely not the same, right? So maybe we can design the shape of this guy a little bit, right? And to make it after sampling, we can get exactly what we want, right? So basically, in addition, on top of it, we can do as follows. So basically, we can design a little bit filter here, okay, and denote it by Q of t. And then with Q of t, multiply this guy, right? And then we do the integral. Okay? How about that? And of course, yeah, here, how to design QT is pretty critical, right? And here we say this QT, and we're going to focus on this, right? Because that is normally what we do in practice. So a word on QT. So QT is normally a device dependent. Function that captures different weighting across the sample. Right, it basically means that for different device, we will have a different QT here, right? Yeah, and the QT cannot be designed, so it's device dependent. So we're gonna design something else to get rid of the impact of QT here. Okay, so now let's see how can we model this process, right? So basically, similar to the impulse sampling. So basically, the process is equivalent as follows, right? Let's say this is our original signal of GT, right? And then, so before we use GT to multiply a train of impulse, right? But here we use GT multiply a train of QT, Okay, so for example, let's say Qt is something like this. It's a very short rectangle signal. And so on. So basically, let's say, so this is Qt, right, for this guy. And the entire thing, right, is a train of Qt, right? So basically, we can write similar to before. So basically, we denote the train of it as QTS of t, where that equals to summation of a bunch of Qt. Okay. And again, so here, basically, the width of it is TQ. Okay. So basically, what we do is that we use this guy to multiply this guy, right? And then we do an integral, right? So now we use this guy to multiply this guy, right? It's multiplication. And then, so we should get something like this. Yeah, here is GT. And then basically, this is what we get. Okay, and we denote this as G hat of t, and then this equals to this guy multiply this guy, right? It's equal to GT multiply QTS. Of t, and like this. And so here, so the width of it is still TQ, right? But the duration from here to here is what? TS. Right, so that's the sampling period. Okay. Okay, and our idea, remember, so our idea, not our idea. So what we can do is nothing but, so this integral is our output, right? So basically, we need to compute the area of each guy, each of this, right? And that is the output of our sampler, right? So basically, the area of each of them is our samples, okay? Right, so this is basically the mathematical process. Is that clear? Okay, and now let's see how we can do the last step, right? So basically, what we do here is that we need to input this signal, okay, into a what? Right, so basically what we want is this, right? And now we have this multiply that, right? So I mean, what we want is this area, right? So basically what we do is that we need to input this guy into an averaging filter to do the integral. Okay, and we denote filter as HA of t. And what is that? Right, normally when we say filter, we say we do a convolution, right? So convolution is kind of integral, right? So basically what we want is to output the area of it, right? And then what is the filter should look like? It's just to integrate itself, right? Then the filter should be like a constant, right? And then the width is basically, we need to just traverse all of them, right? So basically the width is what? TQ, right? So we're just starting from here, and then once we pass here, and then output, right? So basically it's a rectangle signal with a width of TQ. Does that make sense? So this is nothing but like this. So it's so we normalize it a little bit, right? So basically, we don't want any impact of the filter here, right? So the area of the filter is 1. So basically, the magnitude of this is 1 over TQ, but the width is TQ over 2 minus TQ over 2 until TQ over 2, right? And otherwise, it is 0. Okay, so basically this filter looks like this. like this filter. And here's 1 over TQ, right? So this is how the filter look like. Okay, so by the way, so this is a time domain signal, right? So what is the frequency domain of HQ? Oh, sorry, HA. Right, it's a rectangle signal, right? So I think now you're after the midterm, right? So who can tell me what is the frequency domain signal? Yeah, maybe I'll write it in the next line. Sync, very good. What? Say again? What? T over TQ. T over TQ or TQ over T? Yeah. Yeah, that's pi f TQ, right? And then we should have a TQ in front, right? But remember, so we have this, cancel it, and then basically that is the frequency response, right? Do you agree? Right, yeah, so yeah, it's not that hard to remember it, right? So basically it's just pi f multiply the width of it, and then when you take the width of it in front, but here we divide it by TQ here, so we don't have anything in front, right? That'll be it. Okay, great. And after the averaging, and then we just get our signal out, we denote this process as this, right, kind of a sampler. So basically, this is what the sampler that I just described, right? It could be a switch, on and off switch using a capacitor, okay? And this is done all together, okay, right? And then after that, so I use T equals to T K times TS, right? So at this moment, we're going to take this out, and then so we're going to get the so-called G tilde T, right? So that's a sample signal. So that's equals to what, right? After the averaging, we call that what? So after the averaging, we call the signal G1, right? So G1 is after the averaging. Okay, so here is the G1 of T. And then after the sampling process, we take the KTS out, and then that will be KTS times delta T minus. Yeah, and so this is our sampling process, right? So any questions? That clear? The process, right? Okay, so if that is clear, and then let's analyze it. Yeah, I think we got everything, so into all of this. All right, very nice. Let's analyze it. So basically, what we are going to do is as follows. So now we know the Q function, okay, and then we know it's the average, right? And there's some imperfection, introduced by the Q function, and the output of this may not exactly what we want, right? So basically, now we're going to get rid of the impact of Q, okay? So that's basically the idea. Let's see how we can do that. So basically, the very key here is to write down what is G1T here, okay? So and see how we can analyze it. And clearly, we're going to analyze it in the frequency domain, so which is easier. So let's see how we can analyze it in the frequency domain, right? So basically, let's write down the G1 of T, okay? So G1 of T equals to nothing but what G1T equals to? It's after the averaging, right? So basically, equals to G hat of T convolutes with HA of T, right? Yes?
So why do we use the averaging from there?
So we cannot get delta signal. We cannot get a train of delta signal like this, right? Reason is obvious, right? Because it has infinite narrow width and infinite amplitude, right? And as I said, in practice, if we do the sampling, so what we get is through a capacitor, right? So yeah, we need some width of it. Yeah. Okay, so let me see. Yeah, what I want is G1 of t, right? G1 of t equals to G hat of t convolutes with this guy, the averaging filter, right? So basically, let's see how we can do it. So it's equals to HA of t convolutes with the G hat, right? The G hat equals to what? GT times Q TS of t. Okay, and now let's see how we can do it. So who remember how can we deal with this kind of train of impulse when we talk about when this equals to delta? Yeah, we dealt of this problem before, right? Who still remember? Yeah, we may have two ways to deal with it. So one in the time domain, and the other one is to convert everything into frequency domain, right? So in class, what we covered is that if in time domain, how can we think about this problem, right? Nobody remember? Yeah, check your notes, right? So basically what we do is that we do a Fourier series expansion of this. Okay, if we do a Fourier series expansion of this, then we get a bunch of phase shift. And in the frequency domain, it will be a frequency shift, right? That's how we deal with that. So yeah, let's write it down. So basically, yeah, let G now GQ QTS of t that equals to a summation of Qn, right? This is the Fourier series coefficients. Multiply EJ n omega s of t sum over n, right? So that's the Fourier series expansion of QTS of t, right? And if we do that, then we can plug that in here to get HA of t convolutes what? GT multiply this guy. Okay, very good. And here we can basically move GT from here to here, right? Doesn't hurt, right? And now we have a GT multiply a phase shift, right? In time, so that'll be a frequency shift in the frequency domain, right? Then, so basically what we do is that we compute the Fourier transform of this guy, okay, and see what we get. So basically now we have a convolution in the time domain, so it means we have a frequency. We have multiplication in the frequency domain, right? And then we sum everything over n here. And then what we get is we have a Qn here doesn't change. So this GT multiplied this phase will give you a frequency shift in the frequency, right? And Fs. Okay, so that's our Fourier transform. Yeah, any questions? Okay, great. And now let's see. What should we do? So yeah, this is for G1. Yeah, now we need to, so we know G1, so now we need to get this, right? And see how can we get that form. All right, so basically what we did is that we sample this guy in the time domain, right? So here, mathematically, we model that as ideal sampling, right? So we sample this guy in the time domain, then in the frequency, it'll be what? Like make it periodic, right? Let's see how we can do that. So basically, we need to, let's write it down. So basically, G tilde of F is nothing but the sampled version of it. So sample in the time, make it periodic in the frequency. So basically what we do is that 1 over Ts, which is the sampling period, and then we sum it over n to distinguish this n here. So we have G1 F minus MF S. All good. Okay, great. Right, this is what we get. Okay, and for convenience, we make it a plus. It doesn't matter because the m is from negative infinity to plus infinity, right? Plus minus really doesn't matter. Okay, so now we plug this guy in, right? So we know G1 equal to this guy, right? We'll just plug that in here and see what we can get. Kind of complicated. So basically what we get is 1 over Ts. And oh, I missed one thing, right? I missed this. So, oh, I didn't miss this. So we need to compute, we need to know this, right? And I think we computed here. So this guy equal to the sync signal, like this, right? And then we just plug that in. So what we got is a sync. Here, pi f plus m fs, and then we have a tq here, right? And then we need to sum everything over n, and then multiply whatever left here. So it's sum over n, qn, gf minus n fs. No, and I need to plug this in, right? So it's plus f ms minus n fs, yes, right? We have that minus n plus m plus m minus n, right? Okay, very good. Yeah, this is kind of complicated, right? So we are going to make it a little bit simpler. So basically what we do is that we let L equals to m minus n. Okay, so this basically means that m equals to L plus n. Okay, and now let's see what this becomes, right? Yeah, I'll write this. So summation here. So basically what we are going to do is that we're going to replace m by L, right? It's L plus n. For this summation, it doesn't matter. We can just write it as summation over L for all the integers. And then what we got, just copy whatever left. We have 1 over Ts. And here is what? Sync pi. So yeah, this is complicated. So basically, m equals to L plus n. We have L plus n, fs, and then tq, right? And then this is for sync, right? And yeah, and we have, yeah, because of this n here, right? We need to add summation in front. So don't have a lot of space. 1 over, let's say, Ts, and then we need to sum over n here because we have n here, right? And then we have G, this guy, right? And C here, so this is m minus n times fs, and m minus n equal to L. So we have f plus L fs. Okay, so hopefully it makes sense on what I'm doing here. So basically, the goal of doing this is to get this term, right? Remember, so this is kind of what we want, right? Think. So if we do the ideal sampling, right, this term is what we get, and then we don't have anything in front, but if we remove that, this is exactly what we get for the ideal sampling, right? Right, for the ideal sampling, right, we just sample the original signal G, and then in the frequency, we get this multiply that without this term. Remember? Right? So yeah, if QS equals to, let's say, this delta, right, and use this multiply Q, right? So basically, our ideal G F, what do we? I forgot the notation that we use. I just used the G of TS, so that's a sample signal. So that's nothing but this guy, right? Sum over n, for example. Then we have G F minus n Fs, right? So this is for the ideal delta sampling, right? But now this is what we got, right? The only difference is now we have this term, okay? If we don't have this term, we're done, right? But we have this term, so we're going to denote this term as FL of F, right? So this is a kind of a new term we introduced by using, all the effort we have made here. That makes sense? Okay, so, and up to this point, so now we should know exactly what we do, right? Still here we have a periodic signal, but we have the impact of this F function here, okay? So let's see how we can deal with that. So now let me remove this. All right, so yeah, let me see. So this is, this is our, this is our G tilde. Yeah, I denote the G tilde as this guy, right? And remember, so basically, in practice, we use, this is what we covered before, right? We need a reconstruction filter. Okay, so the real G tilde F. Yeah, should I use G tilde? Yeah, this is sample, right? Maybe I'll use something else. Yeah, I'm just thinking what notation I should use. Maybe I'll just use T tilde to consistent with my notes. But this T tilde basically means the reconstruction signal here, right? So for the reconstruction signal, so what we do is nothing but we use another filter PF, right? Multiply what we got here, right, in the frequency domain. So basically, that equals to this multiply. I just use the n here to be consistent with the book, right? There I use the L, right? G F plus NFS. Okay, and so F is basically this function. Yeah, maybe I'll include this 1 over TS in this F. Right? Yeah, let's include that in. So this is basically what I'm writing here. So, and this is for the reconstruction. Okay, so PF is the practical reconstruction filter. That is not ideal, right? As we introduced before. Okay. What time? This is the practical reconstruction filter. Okay, or pulse. Okay, very good. And remember now what we only, so now we need to remove the impact of this guy, right? And remember, so whatever, so this has to be, in order to remove it, so we need to get rid of all the higher frequency component, right? And which can be done using this PF, okay? But another thing, yeah, maybe not, right? Because PF is afterwards. But yeah, what we want is that, so basically we need to kind of inverse the process of F in the baseband domain, right? So basically within the range of our signal, right? So basically what we care is as follows. We care when n equal to 0, where is in the baseband, okay? So F0, you can see it's nothing but 1 over TS with sum over n, and we have Qn here and the sinc pi f plus nfs times tq, right? So this is where f is equal to 0, and this impacts our baseband signal, okay? And here for the signal that we care about is nothing but pf times f0 and multiply the original signal gf, right? So this is what we got, right? And what we really want is g, okay? So we just need to remove the impact of this, and then we're done, okay? How can we do that? Right? So before, if we do the ideal sampling, what we have is the PF multiplied G. Now we didn't do the ideal sampling. What we have is the PF times F naught times G. The only difference is we have this additional term, and this is equal to that. Okay? So basically what we do is we use the idea as we used before. Right? We consider these two together, and then design a filter to do the inverse of this multiplication, and then we're done. Right? So that's basically what we do. And you can see the new filter design is extremely similar to what we introduced before, right? So basically, we design equalizer called EF, right? And so we're going to remove the impact of this and that all together using one filter, right? So which is very nice, right? So design one filter, we can do two things to remove the imperfection of the sampling and the imperfection of reconstruction. Okay, and the requirement is as follows. So basically, we use EF multiply PF and F naught, right? Altogether, so this has to be equal to 1, right? Just want to remove it, equals to 1, right? But remember, we want a time shift of G here, so that's equals to this guy, right? And if f is less than b, and again, so we want 0 if f is bigger than fs minus b, right? And in between, so we can just have whatever, right? It's flexible. Okay, and so basically that's how we design this filter. Okay, which has the same idea as before. Yeah, we don't have time, so we're going to cover about the pulse modulation in the next class. And then we're officially in the domain of digital communication. Okay, thank you.